The aim of this video is to show a more difficult high school level optimization question, and we're going to use the regular strategies, calculus-based strategies for this, and we've got an example as the key part of the video. So it says the strength of a beam is proportional to the square of its depth and proportional to its width. That is, S is proportional to WH squared. Now, the layman's term depth is equivalent to the height H there in the diagram. So we have to find the dimensions of this strongest beam, which can be cut from a log of diameter 60 centimeters. So we're assuming the log is perfectly circular. So we've got our circle there, and the H and the W fit inside the log, as you can see. And we have a fixed diameter of 60 centimeters. I'm going to put in, not the diameter, but I am going to put in a radius of the log, and I'm putting it there because I'm going to use that. So that is basically R, and R equals 30 because diameter equals 60. So what we have is a proportional relationship. We can write that as an equation by changing the proportional to sign to an equal sign and adding in a constant. That's a constant to do with material of the timber material, and there's all different timbers, so there's different K values. So K is a constant, and so I'm just going to write that in there. K is some real number, it's a constant, and we have K, S equals K WH squared now as an equation. So we have two variables, W and H, so the depth and the width. Now I've detected in here a right angle triangle. So our right angle triangle may be drawn as such, which means we may be able to use something like Pythagoras' theorem. And we know it's an optimization question, by the way, because we have strongest, so that suggests a maximum. Okay, so we've got to find a maximum, and it's something to do with this equation here using WH and maybe R. So we've predicted a few things, and we've clarified what we've got to find and what we've been given. So let's go and solve this now. Turning to the Pythagorean part, we have it in that little right angle triangle there. R squared would equal, now see that this purple line here, it's half of the height because we've got the radius comes from the center of the circle. So we've got half of the height squared, all squared that is, because that's the length of one of the short sides of the triangle, and the other short side of the right angle triangle will be half of W, all squared. Since R equals 30, R squared will equal 900. So 900 equals, now we've got inside the pair of brackets that are squared, so half H and half W, if you square the half bit you get a quarter, so that'll be a shared factor amongst the two things. So you've got a quarter outside of H squared plus W squared. Now we can multiply through by 4. We have 3600 equals H squared plus W squared. Now we've got three variables, as I said, up here in this equation, and really we want just to be dealing with two variables based on the mathematics we're going to use. So I've got to eliminate either W or H, it doesn't really matter, so I'm just going to choose to eliminate W. So you rearrange the equation in terms of W. So W squared is H squared minus, 3600 minus H squared. So W squared equals 3600 minus H squared, and therefore W will be the square root of 3600 minus h squared. Now, whenever you take the square root of something, you get a positive or negative, but I've rejected the negative value, the negative result, because we're talking lengths, and lengths are always positive. So lengths are positive, so we reject the negative result. So I'm only talking about the positive of that square root. Now, because we're talking about optimization here, we're going to use calculus at some stage, so it may be easier to write this as an index form situation. So that'll all be to the power 1/2. So just putting a little column here just to organize our work. It's continuing up the top here, so updating our expression for S, therefore S. Now I can call that S of H, okay, so strength as a function of the depth, or H, the height, whatever you want to call it, because this is where we've eliminated W, so I can call it that now, and it's got K, which is a constant, remember, and instead of W we can write that result down here, 3600, etc. I'm going to put in the existing H squared there first, okay, so it's a bit easier that way. KH squared times 3600 minus H squared, all to the power 1/2. So that's S of H. So we need to find S dash of H now to try and find a maximum, or at least find a stationary point. Then we're just going to have to show that it's a maximum. Hopefully this is what we will find. So S dash of H. So be careful here. Hopefully you've been looking after your calculus and you can use the chain rule and the product rule, because that's what I'm going to show you. The methods I'm going to use to show you this one. So we've got the parts of the product are U and V as such. So we've got the product rule. Now just remember, the product rule would be U dash V plus V dash U, and the stationary point is when S dash of H is equal to 0. So I've written in 0 equals. So we're going to follow the product rule on the right hand side. So if U is KH squared, U dash is 2KH. V, write V in, 3600 minus H squared to the half, plus, now V dash, you might need to do this separately if you're not awesome at the chain rule, but it's a function of a function, so it's the inner function times the derivative of the inner function times the derivative of the outer function, and we basically have, for the outer function, it'll be half outside of 3600 minus H squared to the negative 1/2, and that's times by the derivative of the inner function. So 3600 minus H squared will be negative 2H on the inside. Putting that in a set of brackets so it doesn't look like we're subtracting 2H, it's times negative 2H. Alright, so now what we've found there is the V dash. So we've got to write U next to it there. So that's times KH squared. Alright, time to tidy all of that up. So 0 equals 2KH. That. Now plus, did nothing with the first term there. We can tidy this up. If you have a bit of a look there, we've got 2 and a half, and we can times them together, and we can bring that k up the front there, so that becomes negative k, and I'm going to bring the h squared at the back up the front. Okay, and we've also got another h there. In fact, h times h squared is h cubed, so I'm going to write that as a cubed. That's a 3 now, and we've got the 3600 minus h squared to the negative a half there. So what I'm going to do is rearrange now the negative term here on the right hand side. I'm going to add that to both sides, effectively making the left hand side equal to kh cubed 3600 minus h squared to the negative 1/2, and that equals what's left over on the right hand side, which is the first term of the line above, h squared, and that's all raised to the power 1/2. Alright, so that's a squared there. Okay, so we can divide or cancel with things that are common to both sides there. So it's a factor of k, there's a factor of h to the power 1, which will knock that down to a squared. And we've got a negative index, which means it can be put on the bottom there. You don't have to do that. What we could do here is look at multiplying both sides by 3600 minus h squared to the power 1/2, because that, if you times that by positive power of positive 1/2, you've just got something to the power 0 if you use your index laws, and that'll be 1. And the good thing about timesing this side by 3600 minus h squared to the power 1/2, that'll be adding your indices. You have 1/2 plus 1/2 equals 1. So that'll have a index of 1. So that would mean h equals 2 outside of 3600 minus h squared. So that's getting simpler now. And that's 7200 minus 2h squared. So h equals that. Rearranging it, we've got, oh, 1 second, I've dropped my, that's a squared. Excuse me, sorry about that, because back here, that was a squared, I forgot to write it in. Now rearranging, so we're going to add h squared to both sides, so, and oops, oh dear, another little thing I forgot to write in, that's a 2. Alright, so adding 2h squared to both sides, and that makes 3h squared equals 7200. H squared equals 2400. Got to make sure I write my symbols in, otherwise it'll lead to error. And we take care of the h squared equals 2400 by taking the square root, again ignoring negative results because h must be positive, being a length. And you get 48.99 centimeters. And I won't show this bit, but basically if you go back over here to this equation, you can sub in it fairly easily and get a width of 34.64. And so they're the dimensions, and basically that's what we had to find. One last thing that we need to do, probably should have done it back here, but it doesn't matter as long as it's done. We need to just show that stationary point is a maximum. I guess I couldn't have done it any earlier than this. Feels like I've done it too late, but I haven't. So we need to look at values that make to see if it's positive. So we can either check the gradient before and after to see if we've got positive and a negative after, or use a second derivative. So in this question, it's a little bit it's a bit of work, but basically you need to sub into that equation there h values that are a little bit below 48.99, so maybe put in s dash of 48. Just to keep the video short, I'm not going to show you this, but this is what you do. So maybe s dash of 48, and you should get a positive, and s dash of 49, and you should get a negative. Remember, s dash is your gradient function. Or if you like the second derivative, which is what I've plotted here. Now I've taken the k out. If you put a k in there, it will just vertically translate this graph up and down. It'll still have the same zeros, and it will still have the same maximum and everything. So you can use a slider bar of k, use any value you like, or just remove it altogether. And graphically you can see that 48.99, just like in our answer, is a key value. And the reason why I'm saying this is the second derivative is that with the 48.99 there, that's when the derivative equals 0. It's cutting the x-axis, and the gradient of the derivative, which would be the second derivative, is negative at that point. You can see the curve is falling, and basically when the second derivative is negative, the gradients are slowing down, which makes a maximum. So in other words, if we took a sample of the gradients around about the maximum, or around about that turning point or stationary point, basically what happens is that they're getting lower and lower and lower as we sample them, and that's what makes a maximum.